Welcome to another module in this massive open online course. We are looking at convolutional codes, correct? Which we said are a class of error control codes to recover or correct errors that occur over the channel in a communication system, especially a digital communication system. Today let's look at an example of the code generated by this convolutional code. So an example, so let us look at an example of the output. Example of convolutional code. What we want to do is we want to look at the output as a sample output of a convolutional code. So we want to look at the sample output of a convolutional code. So we consider the information bit sequence one 0 1 1 0 0 1. Let me just write it. So this is 1 0 1 1 0 0 1 0 1 1. Okay, 1 0 1 1 0 0 1 0 1 1. So this is obviously x0 starting with x0, x1, x2, x3, x4, x5, x6, x7, x8 followed by x9. Okay, and what we are going to do is, remember, if we start with our definition, C0 of j equals x of j plus x of j minus 2. This is binary field addition, remember, which is given by XOR. We have seen that in the previous module. This is binary field arithmetic. Okay, so this is binary field addition. Now we will realize that to compute C0 of 0, I need x of 0 j plus x of j minus 2, that is x of minus 2. So I will need this quantity. So I need to start somewhere. So what I am going to do is I am going to set both x of minus 1 and x of minus 2 to 0. Assume that the system starts from 0 0. Alright, we are going to see the interpretation of this later. Alright, so what we are doing is we are setting x minus 1 to 0 as well as x minus 2 to 0. Okay, so x minus 1 equal to 0, x minus 2 equal to 0. So this implies C naught of 0, x naught of x of 0 is 1 plus x of minus 2 is 0. So 1 plus 0 is 1. Similarly C1, this is, remember, this is code bit 0 at time j equal to 0. So this is code bit 0 at time j equal to 0. C1 of 0, this is x of 0 plus x of j minus 1, x of minus 1 plus x of j minus 2, 0 minus 2, that is x of minus 2. This is 1 plus 0 plus 0, which is equal to 1. This is code bit 1 at time j equal to 0. Okay, so we have C0 of 0 equal to 1, C1 of 0, that is code bit 1 at time 0 is equal to 1. Okay, now let us look at again C0 of 1, that will be x of j equal to 1 plus x of j minus 2, x of minus 1 x of 1 is 0 plus x of minus 1 is 0, so this is equal to 0. C1 of 1 is similarly x of 1 j equal to 1 plus x of j minus 1 0 plus x of j minus 2, that is minus 1. So this will be x of 1 is 0 plus x of 0 is 1 plus x of minus 1 is 0. So this will be equal to 1. Similarly, and you can go on generating the subsequent code bits at each time instant. Okay. So for instance, C0 of 2, let's generate one more. This will be x of 2 plus x of 2 minus 2, that is x of 0. This will be 1 plus 1. Okay, and binary field addition, this is 1 plus 1 is 0. Remember, we are doing XOR, and C1 of 2 is x of 2 plus x of 2 minus 1, x of 1 plus x of 2 minus 2, that is x of 0, which is equal to x of 2 is 1 plus x of 1 is 0 plus x of 0 is 1. Again, going by binary field addition, 1 plus 0 is 1, 1 plus 1 is 0, so this is 0. So C0 of 1, so C1, I'm sorry, C1, that is code bit 1 at time instant 2. Okay, it's good to remember this. This is code bit 1 at time j is equal to 2. Okay. And therefore, now you can construct. So similarly, do for similarly repeat for other time instants, and what we will get is C0, C1, the sequence C0 we can see is 1 0 0 1 1 0 0 1 triple 1 0 0 1, and C1 is basically 1 1 0 0 0 triple 1 0 0. Okay. So you can see that the resulting code sequence is this. So this is the resulting and one thing you can see is that we have 9 inputs, so total number of, so we have 10 input information, that is counting from 0, so we have number of information bits. So if you look at this, number of information bits equals 10, and number of code bits that are output is 10 plus 10, that is C0, you have 10 bits for C0, correct, 10 bits, and 10 bits for C1, that is equal to 20. Therefore, now again the rate equals number of information bits by number of coded bits. Remember, information bits per coded bits, this is equal to half, and this is something that we have seen in the previous module also. The rate basically is the number of code bits generated per each, the rate is the number of information bits divided by the number of code bits, that is basically the inverse of the number of code bits generated per each information bit. Okay, and here you can see in the simple example that the rate is half, and of course this procedure is slightly laborious because we have to look at xj and we have to compute the code bit C0 of j and C1 of j at each time instant. We are going to see a much simpler and a much more elegant procedure to generate the coded bits as we proceed to the various modules. That is based on the state diagram. Once we construct a state diagram and a trellis for this code, we will see a much simpler and much faster way to generate this code bits corresponding to a given input information bit sequence. Okay. Now let us look at the interpretation. Why is this known as a convolutional code? So if you look at this notion of a convolutional code, so we would like to ask the question, why is this a convolutional code? And to answer that, you go back and look at the generation of the code bit. So you have C0j equals xj plus xj minus 2, which I can write as C0j equals 1 times xj plus 0 times xj minus 1 plus 1 times xj minus 2, which is equal to summation k equal to 0 to 2 h0j or h0k rather, h0k times x of j minus k, where now if you see h00 equals 1, h0 so this is basically your h00, this is basically your h01, and this is basically your h0 of 2. So h0 of 1 is equal to 0 and h0 of 2 is equal to 1. Okay. So I am writing this as summation k equal to 0 h0 of k times xj minus k, and this you can see is nothing but a convolution operator. This is nothing but a convolution, correct? This is a convolution, and in fact this is the filter, this is the filter for the convolution. So you can think of the input, the information bit sequence as being input to this filter H0, which is with filter coefficients H00 equal to 1, H01 equal to 0, H02 equal to 1. Then the output generate the output coded bits, which are generated by the convolution of this filter with the input information sequence. That generates the output coded bits, the output bits C0, output coded bit stream C0. Alright, so it's generated as a convolution of the information, the input information bit sequence with the appropriate filter. Hence, it is known as a convolution code. Okay, so the convolution operation forms a basis for the generation of this code. You can similarly look at C1 of j. Now, it's no surprise there. If you look at C1 of j, for instance, C1 of j is equal to x of j plus x of j minus 1 plus x of j minus 2. This is 1 times x of j plus 1 times x of j minus 1 plus 1 times x of j minus 2, which is equal to summation k equal to 0, again k equal to 0 to 2, this time h1 of k x of j minus k, this is h1 of 0, h1 of 1, h1 of 2. So we have basically in this filter h1 of 0, equals h1 of 1 equals h1 of 2 is equal to 1, and this is, you can see, this is a convolution operation. Convolution, and this is the filter for code stream. Filter for code bit stream, coded bit stream 1. So the code is generated by convolution of the input information bit stream with the suitable filter. Therefore, this is known as a convolutional code. Okay. So let us note that code is generated from a convolution operator. Okay, convolution operation, convolution of the input information bit stream with the suitable filter. Of course, the suitable filter is what determines the convolutional code. Hence, this is termed as a convolutional code. Hence, this is termed as a convolution. So, what we have seen in this module is we have seen a simple example for generation of the bits, coded bit stream of a convolutional code given an input bit stream, and we have also seen the motivation or the reason for why this code is known as a convolutional code, because it is generated by a convolution operation of an underlying filter with the input information bit stream. Alright, so we will stop here and continue in the subsequent modules.